In this video, I'm going to discuss how we can use model-based approaches to something that's traditionally been a document, which is the Mission Requirements Annex. And we're calling this an EMRA. By way of background, the existing Mission Requirements Annex does not appear to be in any kind of standardized format. Many of them are just a few pages, maybe 7 pages. Some are as long as 80, 90 pages. And the MRA does not seem to be aligned with the structure of the existing requirements baseline. That is the standard interface specification or the system performance requirements document. So our proposition is that the MRA could be a model, an EMRA, if you will, and it would be a reference model provided to the Space Vehicle Program Offices and the LSPs for a specific mission. And that structure would parallel that of the requirement baseline so that it would have content that's laid out in a similar fashion to the SYS and the SPRD. The Space Vehicle Program Office would then take this EMRA and populate it, those sections that are applicable, those packages, with mission-specific data, and then that would be sent back to the SE&I contractor, who would then perform calculations to check for things such as interface exceedances within the NSSL system reference model, which models the launch vehicle and the ground segment and operations and support. The bottom line is that MRA as a model would then be able to provide traceability to requirements and to other models, as well as standardizing of the requirements for verification purposes. Let's talk about first the interface data, because these MRAs are broken down into interface requirements and performance requirements. So what you're looking at here is just a section of what's called the containment tree of our EMRA model, and all it is just a series of packages, and that little plus sign indicates that there's content within those packages. So if we unspool the interface data package, which is number 3, you can see that there are sub packages all the way underneath it from 3.1 to 3.13, looking at the various sections that conform to sections of the SYS, for example, mechanical or electrical interfaces, ground processing load factors, shock, vibration, acoustics, etc. So we can further unspool this and look just at, say, the dynamic load factors, which is section or package 3.6. And in here you can see we've got some model elements that we're going to use to structure our EMRA. So let's take a look at a couple of those. So here again is the containment tree, and I've circled two. I've circled what's called a resource artifact 6.1. It's just a model element that holds value properties. In this case, mass in pounds mass, the payload envelope type, the lateral load and axial loads in G's. This is the data that the Space Vehicle Program Office or the Space Vehicle Contractor is going to be providing in the MRA, saying these are the loads that our space vehicle can withstand. This is the mass of our space vehicle. So what we do is we use that resource artifact to classify what's called an instance table in the EMRA. All it is just a table, but the properties, those value properties such as mass, payload envelope, lateral and axial load, what they do is they provide the column headings for the table. And instances are elements that the Space Vehicle Program Office populates in there. Like, for example, in this case, they may have 2 alternative payloads, payload alpha and payload bravo. Both use envelope A outline. They have different masses, and they have slightly different axial and lateral load and g-forces requirements. So this is data that the SVPO would populate in the instance table. And once that's done, you can see the way that eMRA would be used with respect to the NSSL system reference model, because we would have a branch of that model for a specific mission, and it would be traced to the sys and the SPRD, but the eMRA would be brought in and attached as a used model underneath the NSSL system reference model, and would trace to both the sys and the SPRD. And once that's done, we can do traceability. For example, here you're looking at the actual sys requirement for dynamic load factors under acceleration. So there's the text of the requirement. And now we have elements of structure in the NSSL system reference model. This is the standard interface plane, the SIP, which actually satisfies that, and traces to an acceleration analysis block where we have those same, you notice the same measurements that we had in our eMRA. So this is what we're going to take that data from the eMRA and plug it into our NSSL system reference model. We have a parametric diagram within the NSSL system reference model that will calculate an acceleration result, which is either it passes the requirement or it doesn't pass the requirement based on the space vehicle's axial and lateral load requirements in G's, its mass, and the type of payload envelope. The code that you see there is Jython code, and that essentially is a constraint extracted from the text of the requirement, saying that it's got to fit in the envelope that is shown in the requirement. So that Jython code actually does those calculations. But the steps that would be involved would be, once we take in the eMRA table, we can copy the data from payload alpha and payload bravo, and we can paste it into the equivalent instance table in the NSSL model for that particular requirement, in this case the dynamic loads, couple loads requirement. So we've pasted it in there. You can see that there's some additional tables, or additional columns rather, acceleration result, torsion loads analysis, torsion loads result. We're not going to do the torsion portion, but just the acceleration result. And then we can run the simulation within the NSSL model, and it will give us a result. So for example, in this case, the requirement was satisfied for payload alpha, but it was not satisfied for payload bravo, given those particular conditions and under that constraint. So that's one way that we can look at the interface data. The performance data is a similar structure. So we're going to open up package 2. Package 2 contains not every single category that's in the SPRD, but these are ones that, and again, this is all notional, but ones that have we've extracted from a number of existing MRA and IRD documents that we've looked at. For example, launch window is one that commonly appears. So does primary payload mass to orbit, and then of course the orbital parameter options are there that have to be in this section here. So we're going to further open this up and look specifically at the primary payload mass to orbit, and you can see that we've got the requirements in here that are going to then hold the data for the MRA. So as we did with the interface data, this performance data, we're going to look at the requirement primary payload mass to orbit, which is its equivalent in the SPRD is SPRD 010. We're also going to look at orbital parameter accuracy on the same table. So we're looking at package 2.1 and package 2.4. So we put those together in one table, which is classified by both those requirements, and you can see that we now the Space Vehicle Program Office can populate this table with the type of reference orbit, in this case, what the mass to orbit is, what its apogee is, what its perigee is, the inclination, and any of the other orbital parameters, as well as the accuracy on those parameters. So, for example, we can have an apogee accuracy of 54 nautical miles, and so forth. Same thing for the perigee and the inclination accuracy in degrees. So all of these then become instance data inside their eMRA. You can also view the mission requirements as a table. So for example, in our eMRA, each eMRA section contains a requirement element that holds text as well as metadata. So the primary payload mass to orbit would then have text that identifies the parameters required to define the launch vehicle performance as a function of that required mission. So you can see that we've got other examples of launch vehicle capability. So this is language that's taken from actual MRAs, like the mission unique launch vehicle performance. So the text of the requirement, the shall statement, can go right in here inside the model instead of on a piece of paper. So conclusions. The one thing that an eMRA can do is standardize that space vehicle to launch vehicle interface data and performance data so that it aligns with the SYS and the SPRD. It also allows model relationships to other system and requirement and reference models. This is important because that way we have traceability to the requirements baseline. We have traceability because we can interrogate the model. We have traceability to any other model element so that we can do analyses and what ifs and trade studies, for example, if we want to swap out different payloads. A model-based approach to requirements development and management facilitates traceability for both requirement satisfaction and verification. So to be able to have an MRA as input to developing the ICD, or the interface control document, which is really the governing requirement document for a mission, is really crucial because we can then establish that traceability. The modeling tool has simulation capabilities, and they are sufficient for an initial check on any exceedances or limits that are outlined in the requirement documents, such as the SYS. And it provides input for follow-on detailed verification analysis if that's required.